Dear Roger, Carlo, and Conrad, I'm truly delighted to be exploring the depths of imagination with you and would like to invite you to draw out as many personal examples as you feel comfortable sharing with us. First question is about the fact that you're all invested in other disciplines. For instance, Conrad, you derive inspiration from geometry and physics, and your sculptures also necessitate a foundational knowledge of how matter responds, such as steel or wood, and how gravity works. How does being informed by other forms of knowledge production inform your practice?
Thank you, Fatos. I think it all started actually at Oxford. I was at the Ruskin, and that was it was an autonomous art school. It is still within the university. So I was suddenly plunged into the fabric of the university. All my friends were scientists and English students and poets and historians, and the course was also very much outward looking. It wasn't an internal course just studying the history of art and making in jokes about the history of art. It was very much about kind of exploring the sort of his grand history of ideas. So I owed a lot to my tutor there, Brian Catling, who was a real inspiration at the time. But that continued, and I spent a very unusual amount of time in the Science Museum Maths Gallery. Whenever I needed inspiration, I'd probably go there on a weekly basis. It was this very 1960s view of a lot of Victorian mathematics, but I would kind of pore over the artifacts and the objects and the geometries and the cases. So that was a huge inspiration. It's continued now, and I've just done a residency. I've always been very linked to science. I've just been doing this wonderful residency in Nottingham for 10 days, where I've been studying primordial black holes, which was very good timing, so I've been up there and studying kind of black hole ring down and gravitational waves, and it's been hugely inspiring. So I've always found inspiration in things beyond sort of art, and then try and fuse that into my work.
Thank you. Carlo, I want to ask you next, actually. You have a gorgeous choreography of literature, philosophy, and scientific thought in your work. Can you please expand on why you think these disciplines are such good companions?
Let me put it this way. I think there are two reasons. One is that we live in a civilization, a culture. The way we think about the world, about reality, about ourselves, comes from this civilization, this culture, which is made by all these sort of components that include history, science, geography, politics, morality, literature, art, all these pieces. And they make sense if they're integrated, which doesn't mean reduced to one another. It means that they're different perspectives on the same thing which is around us and ourselves. So I have always been curious all my life, I guess in the same way. In my books, I make an effort to talk about this integration. I'm fascinated by science, by physics, by black holes specifically, but I think that makes sense, both for me and for the other people, if this comes into our worldview and informs our worldview, because this worldview keeps changing historically, not only century of centuries, but I would say decades after decades, sometimes years after years. So it's a continuous conversation between the various pieces, the various parts. And I think this is the best way of seeing what is going on in science, in art, just as components of that. The second reason, which I think came very clearly from what you were saying, is that not only there's a different perspective on reality for all of us, but they very much influence one another continuously. I think that, Roger was in strict contact with Escher in its old times. I can't believe this hasn't had an impact in his way of thinking about spaces, space-time and geometry. And it happens all the time, and it has happened all the time. If you read Milton, there is all Newton, Copernicus cosmology, sorry, coming in. If you look at what happened in quantum mechanics, which was happening in the same year as with Braque and Picasso were breaking up reality and perspective. And I, who grew up in quantum mechanics, I'm talking now about reality as different perspectives that come exactly from this combination of things. So I see culture as this continuous exchange in which different aspects of it nourish others. Of course, each one in its own, with its own tools, aims, language, and so on.
Thank you. It's almost like there's a lot of correlation, but the manifestations of them might be different because of the tools, perhaps, that they use, or the areas that they look at. Roger, my question is, like, you worked on two different and very closely related disciplines, mathematics and physics. So you not only can operate between two knowledge fields, that you're also interested in the arts. We will talk about the relationship that Carlo mentioned with Moritz Escher later on. But you also bookended your book, Cycles of Time, with a short story and collaborated with Brian Aldiss on a science fiction novel titled White Morse. What does working within and outside the frameworks of your field bring to your practice as a mathematician, physicist, mathematician?
Well, it's difficult to say. I should explain, first of all, that I have a strong inheritance in the arts, in the sense that my grandfather, my father's father, was a professional artist, and he was he used to paint. This was James Doyle Penrose, and he was Irish, but and he was very strong Quaker family on that side. But you could see he was a very sort of pictorial. I mean, he had wild things, but they were all very religious, the topics. You see, my father very much inherited the artistic side, as did my uncle Roland. He became one of the surrealists. He sort of knew Picasso and many of the other surrealists. He was in with the group there, and became a leading surrealist in this country. I think his father wouldn't have approved of his artistic activity. My father was a good artist, but he wasn't sort of in the professional artist side. He was very good at drawing and painting, and he used to sketch things. He would go out. Sometimes I would join him and do the same, but it was very kind of direct pictorial representation of what he saw. I used to draw all sorts of wild things in my notebooks, completely different, which he would not have approved of, I'm sure. Absolutely wild, distorted human features and so on, all over the place. Except for a little bit alarmed by what I used to do then. I think he wouldn't have liked it at all, but he didn't see them. But I think I was certainly a very visual person. I noticed, you see, when I was an undergraduate, I liked mathematics at school and that sort of thing, and I was supposed to be doing medicine. Both my parents were medical, and but I sort of disappointed them by going into mathematics. And I remember this was at University College London, and they had a rather unusual system. It was a 3-year course, but at the end of 2 years, you did most of the papers. And on the 3rd year, you worked on your specialist topic. And being somebody who was sort of very visual and thinking, and I noticed very much that visual thinking was rather a minority thing in mathematicians. Most people didn't think that way. In fact, it was probably only about 2 or 3 people in the class, well, say, apart from myself, who did tend to prefer thinking visually. I was that sort myself. But anyway, I decided to do 2 geometrical topics for my specialist paper. And I did get a first, but I learned later that my best paper was not in the geometry at all. It was on the algebra paper. And this was because, I can understand why, because I never really finished the geometrical papers. I would see how to do the problem, then I'd have to translate that into words, write the words down. And the sort of translation process going on, I was a slow writer as well. I just simply didn't finish the papers. So I get to think that there was a sort of selective effect against being too visual in mathematics. And certainly when I taught mathematics, I found that the people who think visually are rather in a minority. And I suspect the reason is, more or less what happened to me in a way, is that it's harder to test. So the examinations are much more geared to being easy to do if you're not such a visual thinker. So that was a little disappointing to me. I mean, the really good ones were good at both. Certainly that was true. But in my case, it was very much visual thinking, which was the main thing. And that related to books that I wrote and so on. I like to do all the pictures myself. Certainly my later papers, I think I got fed up with the ones that I was told, no, you have to have an expert to draw the picture. But the trouble is they kept on coming out with mistakes. I said, no, this line goes in front of that line, not behind it. And then it comes back and it's still wrong. So look, I could just do it myself. It's easier. So I ended up doing it that way.
Just a small memory. Roger probably remembers this and knows that I had a great privilege of being in Pittsburgh and sitting sort of in a corner where Roger and Ted Newman, great mathematical physicist, the person who wrote the general solution of the black holes, were working together. And I was, Ted Newman had the office next to mine. So when Roger was coming, I was just come in and sit in a corner and see this. It was absolutely fantastic because the two seemed not to understand each other at all at the beginning, because the way it worked was this. Roger was saying, listen to the, think, you have a four-dimensional complex thing that goes this way, and then you have the other 7 dimensions coming from this, and then you just think, it's a vibration in this, blah, blah, blah. And, Ted was totally blank. Okay, this would go for a while, and then at some point, Ted would say, yeah, maybe, and he would go to the blackboard and say, right side equation, and I would say, is that? And Roger would say, what? He was totally happy. And then they were understanding one another. So I think the science is also this.
I think it was a very good collaboration because we thought so differently in a way.
Exactly.
But yes, that's right. But he had a wonderful skill with having a feeling for equations, which I never really had at all.
Manipulating equations,
right.
turning them around, and incredible.
I want to actually bring an artist in this moment because there's an artist, Cecilia Vicuña. So she has a very strong visceral relationship with words, and as well as like her artworks. She was commissioned for the Tate Turbine Hall, and she basically, for instance, breaks imagination into 2 words, first Spanish, then in English, and suggests that imagination is image in action. But I want to ask, actually, when we're talking about illustrations, maybe, Roger, we could come to your beautiful drawing that of a mermaid that you have made on the occasion of your lecture at the Hans Christian Andersen Academy. The drawing illustrates the quantum and the classical levels of reality. So can you perhaps talk us through?
Yes, well, as you say, this is the Little Mermaid in a sense, based on the story, the Hans Christian Andersen story. But what it really illustrates is, you see, the bottom part of this picture represents what I call the quantum world, where you have all these strange things which are not familiar to people.
Yeah.
And so it's got these strange fish and hammerhead sharks and things like that swimming around, very sort of unfamiliar things. And the top of the picture is more the world we're familiar with. That's the classical world. And the line across the middle indicates the difference between the two. And what's the mermaid doing? Well, you see, she inhabits both worlds in a sense. She is able somehow to bring the quantum world up into the classical world. And she represents, in a certain sense, the big paradox in quantum mechanics, which is the thing called the collapse of the wave function. Mm-hmm. You see, you have a formalism in quantum mechanics, this thing called the Schrödinger equation, and that tells you how the quantum state evolves in time. It just chugs away and follows the Schrödinger equation, except that it doesn't. The world, at a certain point, you have to wheel out of the cupboard a measuring device, you see, and then this performs an experiment. And you get certain probabilities out and you wheel it back into the cupboard again. But you see, that's not following the Schrödinger equation. And it's a big mystery. How is it that every now and again you have to cheat and you change the rules and then you change back again to where you were before? And it always struck me that quantum mechanics doesn't really make sense. And this is you have to accept that it doesn't make sense, I think. The trouble is that so many people in the history of the subject tried to make it make sense as it was. Whereas it seems to me clear that without a really serious change at some point in the subject, you're not going to make it make sense. And so this is really illustrating. You need something else, which is what the mermaid is doing in this picture. She is something that inhabits both worlds and sort of she brings one world up into the other one in a way which is mysterious as far as we know. When we understand the physics properly, it will cease to be mysterious, but at the moment it's not explained by any theory that we have.
Thank you. I will come to you, Carlo, actually on this one, because this paradox is quite interesting. If you think about quantum mechanics, and for instance, especially this morning, we were talking about particles that act like waves and sometimes act like particles, let's say light. And yes, exactly. So how can we imagine something that is so paradoxical as a particle and a wave acting, or neither this and nor? I couldn't ask the question properly, but it's just about...
You did.
Yeah. Okay, perfect. I did great.
We're all still fighting about that. We haven't got to any consensus. Everybody has its own ways about it. I have my own, which of course is the right one. Everybody else is the wrong one.
Yeah, what is yours?
But others have also the same idea that they have the right way. So it's, but that's the beauty of quantum mechanics. It's incredible effectiveness in describing the world and giving us tools for doing all these technologies and allowing us to understand how the sun works, how galaxies were formed, why matter is stable, all sort of. But then when we try to make sense of it, we clash exactly against this difficulty that Roger was mentioning and describing, and come up with an actual understanding of what is going on. We haven't yet, or perhaps we have various ideas that something else different can come in, that we have to look at the world in completely different manners. But so far, nobody's been able to convince everybody else that, and that's beauty, right? We don't have to live in a finished world. We have to live in a, the world is this, because it's one thing, the way we view the world is this incredibly kaleidoscopic jumping around of events around us, which we make sense, thinking that we understand it, because we get used to it. Okay, so what's this? It's a bottle, people talking, and lights. We know everything. So we sleepwalk through this immensity, this beauty, this strangeness, without really realizing how much we don't understand it. And to me, it seems that the best science, and that's exactly what puts it next to the best art, is when it shows that the breaks in our sleepwalking, closed mind, believe that we understand reality, and there's nothing strange. The bottle, my feet, the table is white, and so on and so forth. And then there are these moments in which you see things differently. And you see things differently because, the progress of science leads to Einstein, or because we understand that the Earth is rotating, so we're not moving, we're just turning around. Or because, you look at Vermeer and you say, oh, the light is different. Or you read Shakespeare and you rethink humans differently.
Yeah.
Or maybe you saw and we think differently.
No,
This is the moment in which art and science, in totally different ways and manners, but give us new eyes for looking at the world. And that's, I think, what.
Yeah.
When I was a child, my first inkling of that reality was not as it seems, was provoked and jolted through science and mathematics, and that set me on that pathway, because I've always been excited by the rocks of certainty being pulled out, or the rug being pulled out from underneath me. And with my work, that's always about this the challenge of reality and trying to erode this sense of certainty. But science does that all the time, and maths does that all the time. It's why it's exciting.
But maybe we might be on the eve of this moment. Perhaps it's like a perfect time, Conrad, to introduce your slow arc.
Okay, sure. I can tell.
So buckle up. Don't move from where you
This piece
sit.
was inspired. It comes again from the Science Museum in London. I spent a lot of time there, and I was doing a residency in 2008, and I'd made lots of kinetic works, which by a byproduct of these works, it produced shadow because they were moving light works. But I'd always ignored the shadows just as a byproduct. And then I came across this beautiful Dorothy Hodgkin quote where she described the process of crystal radiography as like trying to work out the structure of a tree by only seeing its shadow. So it was a beautiful, humble quotation. So this is called Slow Arc Inside a Cube, and it's the culmination. It's probably the 11th one I've made, and this one has 3 cages and 2 lights, which move in this sinusoidal way. So the lights accelerate and decelerate. And it's exciting to me because the first one had 1 cage and 1 light, and it was very kind of much simpler, but still had complexity. What's exciting with these pieces for me is that they quite quickly, by the layering, you realize how close to the surface sort of complexity or chaos is, and you kind of the whole room. You can look at the ceiling and the floors and the wall, and you guys are all illuminated with the rhombic tiling, but almost you get almost like the liquidity of water on one side, and then you get this spatial dimensions. I like it also in the context of physics, in that it almost obliterates, in terms of relativity, a true sort of obliteration of the idea of now. There is no present. Everything is being pulled and twisted and stretched in every possible direction, and it will never stop. But I also love this entity in itself, is that you've got this sort of Plato's cave analogy where you've got the sort of shadows of the real. So and the metaphor is that we're the scientists, the artists, we can only see the shadows. But as the viewer, you can see the cage, the Platonic, and the shadows. So you're able to see both. You're put in this God's eye view of being able to see both the Platonic and the shadows of the real. So it's quite a good, useful mechanism for kind of showing the kind of condition of the artist, or the human condition, where we're ingeniously trying to see beyond our perception envelope. But I think I'll leave it there, but we can turn it on later.
That was very beautiful. Thank you. Would you like to, do you have any immediate impressions, or?
Shadows aren't any more real than the thing.
Well, that is a debate. Yeah,
then it is real.
I mean, the shadows of the shadow. I mean, it's you kind of have this. You can have this kind of infinite recession within it. But yeah, I mean, it's yeah. So I haven't shown that to you before. Carlo had a bit of warning about that, but
It's wonderful.
Perhaps we can continue with the Platonic transmigration, the graph that Roger has beautifully drawn. So I want to actually ask about, to all of you, if you have a methodology of imagination when you are thinking about complex ideas and bringing them to some form of clarity. And I personally find this illustration of the Platonic transmigration utterly inspiring, because the drawing is so immediate to convey that a smaller part of the mathematical world encompasses the majority of the physical world. And I think it really kind of like coincides with the slow arc as well. Roger, would you like to introduce us? What was your thinking behind this quite intricate diagram?
Well, I referred to this as 3 worlds and 3 mysteries. And the worlds are the big sphere things, and the mysteries are the connection between the two. So the top thing represents mathematics, and I regard this as having a reality independent of ourselves. We can I think people who are not mathematicians don't quite have the same feeling. I mean, there's a lot of feeling a little bit like archaeology in mathematics. You're sort of digging away in this world and you're finding something, you know, a little wonderful crystal or something like that. And it's all there already. It's not as though we're creating it. So there's definite feeling that it's something out there. So that's the top world, is this mathematical world which has an existence independent of ourselves in a sense. But then it's only a very small part of that world really directly applies to physics. If you know about mathematics, I mean, there are whole lots of areas which seem to have nothing whatsoever to do with the physical world. And a little tiny bit of it refers, we have some wonderful equations which do apply to the physical world. They apply extraordinarily precisely. It's remarkable how well, when you get them right, how well these laws do describe the physical world, but it's a very small part of that. And then again, you see, there is this, the mystery is why is it that somehow the physical world depends so beautifully on these little small part of mathematics. And then you have the world, which is the physical world down there, actual things like this chair and people and all that stuff. But only a small part of this physical world actually has conscious experience. That's the idea. And that is the world down on the bottom left. I've got my right way around, that's left. That's the mental world, which is, you know, conscious experience and understanding and qualities that we use our mentality for. But nevertheless, we are built out of stuff, which is the same kind of stuff as far as we know as everything else in the physical world. It's just organized in some clever way, which brings some other thing out of it. So again, it's only a very small part of the physical world which has mentality. And then the other one is, again, well, most of mentality has got nothing to do with mathematics. You can walk down the street and look at the cars go by. Of course, if you asked about the dynamics of how cars work, that's going back a little bit. But you can appreciate things without that. You can look at the beautiful scenery. You can appreciate the sky and the stars in the sky, or beauty in a flower, or in the bees, or animals and things like that. And you're appreciating them at a quite different level. Without really, you don't need to know what laws are which govern them. And so it's a very, very small part of, well, you see, it's a very small part of consciousness is the idea there, which is actually concerned with the mathematics. You know, even mathematicians don't spend their whole time thinking about mathematics. Some of them probably most of the time, but not the whole time. And so it's a very small part of mentality which is concerned with this Platonic mathematical world, and they explore all sorts of parts of that world which have nothing to do with a little tiny bit which is concerned with the physical world. So it's described as a kind of paradox. It's drawn as a paradox also, because it's sort of an impossible triangle. You see, each bit of it is coming out of the other bit and coming towards us, and it's impossible.
It's an Escher staircase.
So you couldn't construct that out of rods and spheres and things. So it's meant to be a deep puzzle beyond all the little puzzles which are involved in the whole picture.
But I think what is striking is that it's a very simple diagram, but at the same time you can write volumes about what this diagram would mean and what it would correspond to in all worlds.
Its implications are massive.
Yeah. So maybe we go, yes.
Roger, do you think that in the Platonic world there is more than mathematics?
No, that is supposed to be the I mean, it depends what you mean by mathematics, but it is meant to be mathematics. That's what it is. And it's only a small part of it which has anything to, I mean, just, you know, that we have a certain equation, you know, Einstein's equations or Newton's, Galileo, and a few things which have to do with
things that are in neither of these three worlds, which are even out. Do you think there are things that are outside these three worlds? I don't know, some people.
Well, not, I mean, that is the mathematical, that's what that sphere represents.
Okay.
I'm not saying there's mathematics outside mathematics, because it's supposed to be mathematics. That's what.
No, but are there Platonic things which are not mathematics?
Oh, I see. Well, that's a different story. Yeah. Yeah. No, I'm talking about the Platonic mathematical world there, yes. I mean, you can consider other things have Platonic existence, but then maybe you follow them down into one of those other worlds, you see. Yeah, I mean, in a sense, the whole picture is a sort of, you might say the mental world has this Platonic aspect.
But it says morality has its own Platonic world, or
no, I agree with that. Yes, morality is not up there. Yeah.
Okay.
I think I had another one which had a sort of thing up. I can't remember, somewhere.
It's coming.
Oh, it's coming. Yes. Yes, I think there was another picture. Yes.
We might fast forward, but this is also a drawing by Conrad. I don't know if we should go into it. Perhaps we can.
Yeah, no, we don't need to. I mean, it's up to you, whatever you feel. But
And maybe I will actually jump to Carlo,
Yeah.
because
Drawings by me, because
you have a drawing as well. We found it. I mean, it's much more of a graph that you've actually. This is from the lecture that you gave in India. It's actually where you met Roger, I think, in the beginning of 2000s. And this was your research about the scientific papers and the topics that the scientific papers were mostly addressing in that research center. My question is not necessarily the explanation of this graph. It also, of course, quite is interesting about like the fashions in science that, you know, Roger also addresses. But do data present you an interesting kind of like platform, creative platform to build your ideas? Because I read about this lecture that was quite a striking lecture. Like, is this graphs or data, are they your illustrations in a way?
well, this is a proof that the fashion has nothing to do with good science.
Just the number of people who think about these different topics.
Yeah, this is a number of papers published by year
Yes.
of these three
So you
topics
see, string theory was way up there.
at the time. Now it's much
And you
lower.
see, that's the majority at that time. I hope there are not so many now.
It's not
The
anymore.
one at the top was the majority point of view at the time of where physics is supposed to be going in a deep level. So those are the string theorists up there. And then Carlo's one was the middle line. That's the loop quantum gravity theory,
right.
as far as I can remember. And then I'm sort of creeping around at the bottom. That's twistor theory at the bottom there, I think.
Yeah, that's right. That's right. No, but yeah, I mean, data is it's also the thing that nourishes science, but data has to be. Science is not just looking at data and taking things out of it. Obviously, it's much more complicated operation. Not only because of that, but also because
It's the fashions in the world. That's basically.
yes,
Yeah.
yes,
It's
and
not so much about truth.
yes, fashion is not about truth, and Roger has a book in which is discussing this thing here, and I think this
Explain the Italian translation of the title of that book.
moda of fashion.
It doesn't have anything to do with the actual title. But that shouldn't go into that.
Yeah, yeah.
But
Okay.
that's a very. But in terms of this imagination and things, the interpretation of data is really how, because it's so many people. There's so many ways you can interpret and represent data and information. But so that is sort of key, and I guess in terms of where the human element comes in.
The data, science builds on data. It's not, and you know, even a super abstract thinker like Roger think about eons of universe that repeat themselves, and then looks for data in the sky, in the distribution of things in the that come from the sky that support this and try to interpret it. But data needs to be interpreted, and the way we interpret it's completely not clear. Let me give an example, which I think is a major example. Science was defined, mathematical science was defined for several centuries as the following. We see things moving in the sky, okay? Mars, Venus, the planets, the sun, the moon. Find simple movements that make sense of this strange movement. Mars goes back and forth between the stars and does silly things. So find circular movements that reproduce this movement. An astronomer played this game for centuries, including Copernicus, until Copernicus and Kepler just changed the game and said, instead of this game, find a combination of circles that make sense of what we see, change the story completely. For Copernicus is maybe what we see is because we ourselves are in motion, and for Kepler, let's forget the circles and find an arbitrary mathematical curve that is not circle. So this is an example in which the problem was completely redefined, the problem of what it is to do science. And at different levels, it happens all the time. And I think I know very little about the history of art, but what it is to do art has been redefined at every generation, right? What are we trying to do when we do art? So
Do you think that Copernicus took when he had this radical paradigm shift where things swapped round? Do you think it was because he saw it in the numbers that we were in fact revolving around the sun, which was an unimaginable idea at the time?
No.
Or do you think he just had this
No,
radical imagination?
No, I think he was a Polish. He came to study in Italy during the Renaissance. His friends were some of the artists and the thinkers of the early Renaissance. It was this complete cultural, strongly cultural movement of let's do everything anew. And he was deeply influenced by the culture around him to do everything anew, on the one hand. And on the other hand, it was not so, it was an idea that was in the ancient literature. He found it in the ancient literature. So it's a combination of the courage of thinking completely different and a deep knowledge, finding ideas and recognizing a good one. Kepler is the opposite. And that's, again, there's no methodology, I think, in doing art, and there's no methodology in doing science. Kepler, it's one of the most incredible stories because he was using the Copernican system with circles, okay? And Mars, he was working on Mars, and Mars moves according to the Copernican circle theory as a circle of a circle, an epicycle for different. Except that he didn't have computers, so he had to do everything by hands, right? It's computing the movement and checking with the data. So he decided that the circle of a circle, because of the peculiar thing of Mars, could be approximated by an ellipsis. So he was using the ellipsis. Ellipsis is easy mathematics to work with, easier than two circles, one on top of the other. So he was using the ellipsis as an approximation to what he thought was the real thing, which was circle of a circle. And then at some point, in checking the numbers with the numbers that Tycho Brahe had measured with, he realized that when he was doing the correction from the ellipsis to the circle of a circle, he was going away from the data instead of toward the data. So he said, wait a minute, what I consider an approximation works better than what I think is the actual thing. So maybe I should throw away the actual thing, just keep the ellipsis. So this is a case in which it's an example of the infinite amount of human stupidity. I mean, somehow nature had to put the ellipsis in front of his nose. It's like, idiot, look at there is an ellipsis, it's there. Just look at it, you're already using it. Before he could actually see it into the data. He was not seeing the ellipsis into the data until the actual correction away from the ellipsis was taking him away from reality.
I will go on to our next slide, which kind of connects with the circle in a circle, but this is the depiction of the loop quantum gravity.
I didn't do that. Francesca did that.
Okay.
She did that.
No, it's not Carlo's drawing, but perhaps, following on Kepler, could you perhaps talk us through what is loop quantum gravity?
Yes. So first, let me talk about this because so in my answer, I got to connect to Roger idea twice. So the first one is that this is a picture of one of the predictions or consequences that seems to be coming out from loop quantum gravity, from the equations actually. When you apply the theory to cosmology, and if you go back in time, you start from the bottom here. This is a big, large universe. You go back in time, and we all know that the universe in the past was smaller and smaller and smaller. And what the theory seems to predict that if you keep going back in time, you don't just disappear at a point, but you have a previous phase where there is a contracting universe. So what happened at Big Bang is a sort of bounce. Are we sure that this is the case? No. This is a possibility that seemed to be indicated by loop quantum gravity. There are other possibilities. One is that the universe emerged from nothing. And one is a possibility that Roger had been studying a lot recently, that also there is a previous universe, but it doesn't need to contract to rebound. There's a different kind of mechanism through which expands a lot, and then in some sense we start again. And so that's about this picture. It's about trying to use what we know about nature today to understand what happened at Big Bang, and before, and maybe in the future. Now, the theory we used for this is loop quantum gravity, which is a do you want a few lines version of loop quantum gravity?
Yeah, very crisp and crystallized, please.
Okay, so that's my second connection to Roger. Roger, a zillion years ago, had pulled out of the sky a complete intuition about possible mathematics for describing quantum space-time, because loop quantum gravity is an attempt to understand how is quantum space-time. And he called it spin networks. And this idea that there is a mathematical structure, which is a network, so little links connected to one another, nodes, a network. Spin, because the mathematics has to do with rotations, with spinning, so you attach these things, quantity spins, which are related to theory of rotations. And that turned out to be a main mathematical tool years later, when Liz Morning and I worked on trying to make sense mathematically precisely of loop quantum gravity. We found Roger spin network into the mathematics which we are working. Technically, they define a basis, the Hilbert space of the theory. So this gives the intuition of the description of space-time that comes from loop quantum gravity. If you look at the very small, here space, so this is a piece of space, you go smallest one, smallest one, smallest one, small, much smaller than atoms, much smaller than nuclei. If the theory is right, what we expect is that we see something similar to the mathematics of Roger, namely a discrete structure, little nodes, quanta of space, like light is quanta of light, connected by links, namely they knows who is next to whom. And so this discreteness of space is the core of the intuition, or the visual intuition, if you want, of loop quantum gravity. And the subtle point is that this network, you shouldn't imagine it in space, a space with a network inside. So forget the space. There's only the network. And what we call space is sort of the network seen from a large distance, like a T-shirt it's a network seen. It's continuous only if you don't look at the details. So this granular structure of space, it's predicted by loop quantum gravity and is the main intuition about reality that comes from loop quantum gravity. And the math comes from that guy there.
That's amazing. Actually, perhaps, Conrad, it's the perfect time for your question for Roger.
Oh, well, yeah, I've been thinking very, very hard about the one question you would ask Roger Penrose, and it's been yeah, it's sort of like a fairy tale sort of moment, but it's so the question I wanted to ask you, I imagine that you came across black holes 80 years ago as a young boy. You probably, for the first time, encountered the idea of them as a notion, as a vague theoretical idea, and it's probably safe to say no living person understands black holes better than you do. And I guess the question the question I wanted to ask you is that is about the future. So it's about the imagination, and it's about what you think will be revealed. There's so much now ability to sort of through interferometry and all these amazing techniques to sort of observe them, of collisions and of a ring down. What do you think the next 50 years will reveal about black holes, and are they a source? How should we as laymen respond to these entities, these extraordinary, powerful, destructive? But for me, they sort of fill me with hope. It's like discovering a new world. But what does the future hold? What do you predict will be discovered?
Well, may I first slightly correct what you were saying about when I first thought about these things? It was when I was a graduate student. No, it was before. It was a research fellow. I was a research fellow in my second year as a research fellow at Cambridge St. John's College. And I had a colleague who taught me an awful lot of physics. I learned mathematics, but then Dennis Sharma was a very good friend of mine. And I learned an enormous amount of physics from him. And he heard about a lecture that was being given at King's College in London. And he drove me to this lecture, which was being given by a person called David Finkelstein. And he described basically what we understand by a black hole, in the sense that, you see, people previously had been very confused about this thing that referred now as a horizon. You have this region which you can fall into, but you can't get out again. So it's a one-way barrier, if you like. You can fall through in one direction, but not the other. And it really hadn't been understood properly by people, I gather, until David Finkelstein. I thought other people like Lemaitre and so on had, but apparently not really. According to Dennis Lemchol, who's a historian on these things, he tells me really it was Finkelstein who first understood it. And I went to this lecture he gave, and it was a real revelation to me. And so I began thinking, gosh, I wonder if there's a theorem which shows that you can't avoid these things. This was a long time before I found a theorem of that sort.
58.
1958.
You mean Finkelstein lecture? Yes. That would have been 58, I think. That's right. And I began thinking, wonder if there's a theorem which shows you can't get rid of this horizon thing. You can't get rid of the singularity in the middle. You've still got this place where things go wild, right in the middle. And it wasn't at what people thought was the singularity originally. That's gone into the middle. So I began to think, is that one in the middle something you can't avoid? And then I started thinking, well, I wonder if there's a theorem. Never heard of such a thing. And I began to think, what do I know that other people don't know in this area? Two-component spinors. So this was something I heard about from Dirac, the great physicist Dirac. When I went to his lectures, various lectures were nothing to do with what I was supposed to be doing. I think there's a moral there. The 3 courses that I went to when I was a graduate student, I went to 3 lecture courses which had absolutely nothing to do with what I was supposed to. One was by Hermann Bondi on general relativity, which had a big influence on me. One was Paul Dirac on quantum mechanics, and I learned about the quantum superpositions and that sort of thing, and was very puzzled by it. And the 3rd one was by a lecture course by a man called Steen on mathematical logic. And I learned about Gödel's theorem and how you could see the truth of certain things that your methods of proof wouldn't get you to. And I found that absolutely stunning. So that these things influence me in ways. I don't know what the moral is to all this. But it certainly was things that were nothing to do with what I was supposed to be doing. I did write a thesis, which was more or less what I was supposed to be doing. But it was these other lectures which really had a bigger influence on me. And certainly the Finkelstein lecture was just as a seminar.
And the future. If
So you want to know the
if you
future,
dare
yeah.
to if you dare
No, you see,
to hope
that's
for what we will find.
well, I can give you you see, it's not the future because it's already written up in papers. You see, I have a theory. And there's a long story which I probably shouldn't go into here because it's. You see, I had this theorem about singularities in black holes, which was in 1964 or something. I went to I gave a lecture in King's College, London, same college as the Finkelstein one, much later. And in 1964, I guess that was, the paper came out in 65. That was the paper which I suppose eventually got a Nobel-prize. Took a little while, but still, it was. I've heard of longer. But what was I trying to say? Yes, you see, this tells you that basically in gravitational collapse, which is what happens when you make black holes, you have these singular places where the theory goes wild and it just goes crazy. But fortunately, it goes crazy behind these horizons, so you don't worry too much about them. But there's also a place where the universe apparently went crazy by itself, which was the Big Bang. And Stephen Hawking picked up on these techniques I was using, and he started to prove theorems which had to do with the Big Bang. Are they generic? Can you get away from by wiggling and making them more general? Maybe there was a collapse which swished around and came out again. And those results showed, no, that doesn't work either. So you have singularities which you can't get rid of. So they seem to be the same thing. but they're not. They're utterly different. The ones in black holes have an utterly different structure from the Big Bang. And it took a long time for me to appreciate this. And I remember not realizing it for a long time. And I remember seeing Jim Peebles in a car going up. He got the Nobel-prize the year before I did on really understanding the early universe. And he really understood the early universe backwards. I don't know if that's the wrong way of talking about it, actually. But and I remember worrying about why all these solutions that mathematicians had come up with, different kinds of singularities, and so why don't you cosmologists think about these other solutions? And he looked at me and said, because the universe is not like that. I thought, my God, it's not, is it? And so I realized it's completely different. And the question is why? And is that something to do with... No, well, it's very hard to see, because I used to think it's got to do something with quantum gravity. Why are they so different? Why are the collapsed singularities so different from the Big Bang singularity? Big Bang mass is absolutely uniform and completely, the gravitational degrees of freedom are completely wiped out for some reason. And no explanation was coming out about that. I thought, well, maybe it's quantum gravity, like most people thought. But then it has to be a very, very peculiar kind of quantum gravity, which it is, I suppose. I think it is very peculiar. But I couldn't really make that work until really I was starting to use conformal maps. So when big and small behave the same way. And Escher does. Did you have a picture of an Escher?
Yeah, it's coming up.
Yes. Well, you can see that in a minute. Yes, or it's up. It describes, well, it's a kind of geometry that's more or less irrelevant to what I want to say. It's a kind of geometry called hyperbolic geometry, but it doesn't matter too much what kind of geometry it is. The point is that the fish, or whatever, they're sort of like fish creatures, the main thing is look at their eyes. They're circles, and they remain circles. They seem to get smaller and smaller right up to the edge. Now that edge around the boundary represents the infinity of the world that these fish creatures inhabit. But the representation is what's called a conformal. It's due to a mathematician called Beltrami. Well, Beltrami was first, Poincaré rediscovered it later. And this Beltrami representation of this kind of geometry is very nicely represented by Escher. And you can see by looking at the eyes of the fish creatures that they're circles. They remain circles, no matter how close to the boundary you get. And more or less, it's saying that shapes remain precisely. Small shapes are precisely illustrated, but size is not. They can be big or they can be small, but the shapes, particularly the small shapes, remain actually drawn. And these lines drawn here represent what are the straight lines of this geometry. So it's a kind of geometry where you can squash things down, and big and small behave the same. And the thing is that you can do the same thing with physics, so long as there isn't any mass around. And this applies particularly to electromagnetism. The wonderful equations that Maxwell produced describe electricity and magnetism, fits it all together, and you can see light comes out of it. So light is hidden in these equations. Wonderful, absolutely fascinating equations. And they are conformally invariant. So big and small, you can do one of these tricks, squashing that I have here, and the equations work just as well. Yep. What makes the difference, well, when you can tell big from small, is when you have mass. And this is combining the two most famous formulae of 20th century physics. What are they? Einstein's E equals mc squared. C is just a conversion constant. Tells you that E, energy, equals mass. Energy and mass are equivalent. Even earlier than Einstein was Max Planck. He produced a formula, E equals h nu, or hf. Nu, or f, is a frequency. Max Planck tells us that energy and frequency are equivalent. Put the two together, mass and frequency are equivalent. So if you have a mass, it is a clock. Every mass has a natural frequency attached to it. It wiggles very, very fast, so it's much too fast for an ordinary clock, so you have to gear it down. And you gear it down, and you have these wonderful clocks, which now we have. atomic and nuclear clocks, which are extremely precise. And they come down to this fact that a mass is a clock. The converse of this is if you don't have mass, you don't have clocks, you don't have scales, you don't know big from small. And the two places in the universe where I claim you don't have clocks are one at the Big Bang, because at the Big Bang, energies get so huge that the mass becomes irrelevant. The energy in the particles moving around so fast is in their motion. And the fact that they have mass is neither here nor there. So you lose the scale at the Big Bang. Where's the other place? In the very, very remote future. You have to talk a little bit more about that. I won't go into the details of that. But basically, it's dominated by photons. Photons don't know the scale. They don't have any mass. And so in the remote future, so the argument goes, again, you lose the scale. So at these two ends, the Big Bang and the remote future, the universe doesn't know how big it is. So my idea was to stick one of these things, Big Bang to remote future, onto another one, another Big Bang, remote future, and another one. And that's my conformal cyclic cosmology, which I claim there is actually a fair amount of evidence for. You can actually see through into things going on in the previous, what I call eon. Our eon, cosmic eon, if you like, began with our Big Bang. Certainly the Big Bang was there. I'm not complaining about that. Although I was brought up on the steady state model where Dennis Sharma used to try and persuade me, quite convincingly he did, that the Big Bang was a fake and it wasn't there. There was a good reason for it, which came from a mistake in the observations. Never mind about that. But the Big Bang was there. And that's the beginning end. And then what's the remote future? Well, it just expands and expands and gets less and less dense and becomes more and more boring. And I began to think how boring this remote future is. And then I began to think, well, who's going to be around to be bored by it? Only photons pretty well. And it's very, very hard to bore a photon. Not just because it probably doesn't have experiences, but more importantly, because it doesn't experience the passage of time. From creation to where it gets absorbed is 0 time for a photon. That's just relativity. So photons don't experience the passage of time. So they go right to infinity and come out the other end. So that was the picture.
That was brilliant. Thank you so much, Roger. I want to actually connect to also what Carlo was saying about the loop quantum gravity theory about there's a correlation.
Yeah,
but what I want
was
to
hinting at that when I said the
network.
universe that bounces back, it's only an hypothesis. There's another possibility, which is exactly what Roger described so far, that the universe sort of loses notion of size and then restart again from a Big Bang without notion of size.
But perhaps we could add a little bracket about your also kind of conception of time, because you say time is local and in a way very much kind of like in parallel to how Roger was saying a photon will be bored because the time will be quite vast.
But it has no time because it has no mass, so it doesn't experience any time. It's nothing.
Yeah, maybe actually, yeah. So is time real, Carlo, or is it a construct of our imagination?
No, time is not real. So I'm going to give you a 12 hours lectures about it.
Yeah, sounds great. I think you're all cozy here.
Careful, because just one thing.
No, only 2 minutes.
No, just half a minute. This is danger in taking sentences out of context, of course. Time is not real in some sense. It's very real in some other sense. That's, I mean, it's, when Roger says that a photon doesn't experience time, of course, he's saying something scientifically very precise, which can be easily misunderstood for something which is not being meant. Not what we speculate strange about the world, but what we know for solid, which is what we call special relativity or general relativity, it's a vast modification of the way we know time works in the large universe, which has as an effect that our usual notion of time is not good for talking about these things, okay? And is of course not good for talking about the other possibilities. So our common notion of time, which is the same for everybody, becomes old at the same rate, and so on and so forth. We know that's wrong. Okay, the time that we use for talking about the notion of time that we use in our daily life is not applicable neither at the scale of the cosmos nor the scale of the small atoms, and so on and so forth. This doesn't mean that time of our experience is not real, in the same sense in which I can say, you know, the square around here is flat. And if you say, well, but the Earth is not really flat. Okay, yeah, sure. But that doesn't mean illusory, the flatness of the... It only means that it's approximate. So time is very real, but if you look more in detail how it works completely different from our usual way of thinking about it.
On that note, I want to thank you all. It's been a really fascinating and slightly puzzling conversation. So I hope you have enjoyed as much as I have. And thank you, Carlo, Conrad, and Roger. Thank you all for coming. As Daryl has and John has informed you, we have some more food for thought, much more casually. It's going to happen in the foyer. Thank you again. Our next lecture is on the 28th of September. So if you want to watch this series, please come back. Thank you.
Thank you, Fatos.